Hello, students. We are getting into the second to last chapter, which in Greek means the penultimate chapter, and I'm pretty excited about it. We're going to be simplifying radicals. This is something that is brand new and you have not seen before, I guarantee it. So our essential question is, how do I simplify square roots that are not perfect squares? And we'll look at what that means. Here are some hilarious memes. I'm hoping to entice you with them to watch my video. Here's one of my all-time favorite television characters, Dwight K. Schrute from The Office. Are you interested in watching now? Hope you are. So just a review, what's a square root? It's a number that times itself gives me that number. So like the square root of 25 is 5. Why? Well, because 5 times 5 equals 25. Notice that square roots are the opposite of squares. 5 squared equals 25. Therefore, the square root of 25 equals 5. So I'm going backwards of square roots. I'm seeing a number that multiplies by itself to get me that number. Okay, so sometimes we have things that aren't perfect squares, right? This is a perfect square because the square root is a nice, easy whole number. But the square root of 27, I would need my calculator to do this, right? I would need a decimal. It would be 5 point something, maybe like 5.2. Let's see how close my prediction is. I'll pull out my calculator and actually do that. The square root of 27, oh my goodness, I was literally right on. Rounding, it's 5.2. That makes Mr. Gregory a happy man. And you can ask yourself, did he do that beforehand and just trick us into thinking he's really smart? Or is he actually really smart? I'll let you decide. Okay, so here's what we're doing today. We're going to learn a way, instead of getting a decimal for root 27, we're going to learn a way to simplify. And it's just like simplifying fractions. If you put into your calculator 6 divided by 8, because that's what a fraction is, it's going to give you the decimal 0.75. But I know that I could also reduce 6 over 8 to 3 over 4, and like on a test, typically, I would accept either of these answers, right? Or I might say, hey, write your answer as a fraction. So I could either simplify the fraction, or I could just do the math and get a decimal. So it's going to be the same thing with square roots. I could put this into my calculator and find that this is 5.196152432, blah, 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 blah. But because sometimes in math I want to leave things exact, I need to find a way of simplifying it. And here's what we're going to do. We're going to look for perfect squares that live within 27. So let's think about what different perfect squares are. I have 1, that's 1 times 1. I have 4, it's 2 times 2. I have 9, which is 3 times 3. And let's stop right there. Because I know that 27 is a multiple of 9. I know that 27 is 9 times 3. Are you okay with me writing this? Like, I haven't changed the problem, right? I've just rewritten 27 as 9 times 3. But isn't it true that I know what the square root of 9 is? So here's what we're allowed to do. There's this rule that says if you have a square root, square rooting a multiplication, you're allowed to distribute the square root. This is something that I'm allowed to do. I'm essentially distributing the square root. And now notice, I know that the square root of 9 is 3. Do I know the square root of 3? No, so let's just leave it as the square root of 3. And I have this new, more simplified answer that I read as 3 root 3. What did I do? Well, I found a perfect square that lived inside of 27, and I was able to take the square root of just that. So this is kind of weird. Let's do a couple more examples. Remember, in order to simplify these, I'm going to look to see if there are any perfect squares inside of these numbers. So it would be really good to have your perfect squares memorized. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. I'm just going to keep listing them because these are all perfect squares that you should memorize for the purpose of looking for them within other numbers. I'll go all the way up to 13 squared, just in case you got lost. The big numbers are hard, but I'll go all the way up to 13 squared. 13 squared shows up just enough that I like to have it memorized for myself. Okay, so let's look at the square root of 50. We need to see if any of these numbers are inside of 50, are factors of 50. I think 25 is, right? 50 is 25 times 2. So instead of 50, let's write 25 times 2. Now I can distribute the square root. And what's the square root of 25? Well, it's 5. And I don't know the square root of 2, so I can't take the square root of that. But since I could take the square root of 25, I have now simplified. Nice. Let's look at 20 next. I'm looking at my list of perfect squares. Here are my eyeballs. They're looking over here. I have some eyelashes. I see 4. 20 is 4 times 5. So if I write 20 as 4 times 5, I know the square root of 4 is 2. And I don't know how to take the square root of 5, so I'm going to leave that underneath the square root because I don't know how to take it. Last, let's use our eyes. We're looking at 700. This is a really big number. I definitely know that 25 is a factor of 700, but I think a much bigger factor is 100, because isn't it true that 700 is 100 times 7, right? That makes a lot of sense. That's easy. So remember, I can distribute the square root. I know how to take the square root of 100. That's 10. So square root of 700 multiplies 2. You would read this 10 root 7. Get used to saying that properly. Now I need to teach you a new technique because sometimes the numbers won't always be this obvious. So we need another technique for these new ones, and we also need a technique for dealing with variables. So notice each of these numbers are very complicated and they also involve variables. So here's the technique I'm going to teach you. It relies on this fact. All right, see if you can figure this pattern out. I know the square root of 25 is 5, right? Isn't it true that isn't it true that 25 is 5 times 5? So I can say that the square root of 5 times 5 is 5. Isn't it also true that the square root of 6 times 6 is 6, right? Because 6 times 6 is 36, and I know that the square root of 36 is 6. So if we continue this pattern, basically, as long as I have a number times itself, when I take the square root is just that number, right? So similarly, the square root of x times x is just x. Why? Because the square root of x squared, well, aren't those opposites? They cancel, and that leaves me with x. Okay, so I'm going to use this fact, and here's what I'm going to do. I'm going to factor each of these numbers. Now, we did factoring with polynomials. We made the parentheses, but here when I'm factoring with just regular numbers, remember that we do that by making a factor tree. And I'm going to do it both for the variable and for the number. So let's do it for the variable first. This is x times x. That's easy. Now let's do it with the number. Factor treeing. Since this is an even number, I know that it's definitely divisible by 2. And when I divide this by 2, I get 81. Now, some of you might recognize right now that 81 happens to be a perfect square, but I'm going to keep going with my factor tree to illustrate the point. 81 I know is 9 times 9, and each of these 9s is 3 times 3. And I am now at the bottom of each of my branches, so the factorization of this is each of these. So I'm going to rewrite the square root of 162 as 2 times 3 times 3 times 3 times 3 times x. Literally write it all out, because here's what it's going to help me with. Every time I see a pair, I can take its square root. So in other words, I have 3 times 3. That's the square root of 3 times 3 is 3. So this square root is 3. Also, I have another pair of 3's. This square root is also 3. So these two 3's, I've taken the square root of them. I know the square root of x times x is x. And this sad, lonely 2 does not have a square root. It gets left under the square root because I could not take the square root of it. Now let's just clean things up. This multiplies to 9, and I can get rid of those bullet points. So here is my final answer. Whew, complicated. So remember, what I did is I factor treed, that's this, and then I was looking for pairs, because each of the pairs I can take the square root of. I know that the square root of a pair is just that number. Now, I see this common mistake. Typically, the mistake I see is that when people identify the pairs, they write them underneath the square root, and then the lonely one they write outside the square root. Don't do that. If you take the square root of a pair, it comes outside the square root. If you don't take the square root, it stays under the square root. So just make sure to keep things split up that way. Okay, let's do 2 more examples quickly. Actually, time's getting a little long, so forget this example. It's a big number. We'll practice more with big numbers in class. Let's just do this final example. All right, x cubed is x times x times x. 75 is a multiple of 5, and I think if I divide 75 by 5, I get 15. 15 in turn is 3 times 5. Okay, so let's rewrite my square root as 3 times 5 times 5 times x times x times x. And I'm looking for pairs, right? So I have a pair of 5s. The square root of 5 times 5 is 5. So it's now outside the square root. I'll write the square root over here just so we can keep things straight. The square root of x times x is just x. And what was I left with? This guy doesn't have a pair. It's still under the square root. This guy doesn't have a pair. It's still under the square root. Let me just write my answer a little closer to each other. My final answer is 5x root 3x. Yes, that's how you read it. 5x root 3x. Okay, tricky. So just a summary for the tricky problems. Factor tree, look for pairs. Pairs come outside the square root. Thanks for watching.